All right, let's get started on today's lesson. Today we're going to be learning about probability identities, and it's a bit important that we learn about some of the formulae that we use, because remember, we are calculating for probability. Hello, Fortunate. And probability gives us an answer. It gives us something, or the number of events of that particular event, or over the number of possible outcomes. But some of these outcomes are a little bit different, and we've seen that when it comes to Venn diagrams. So we're going to put a little bit of formula to it. All right. So first thing we're going to do is we're going to look at these probability formulas. I would like you guys to take a screenshot of this. If you can, if you can't, quickly write it down. The very last one, the one with the probability A/B, not that important at the moment. It's called conditional probability, which is something that we will talk about much later. I think it's even a grade 11 thing. It's no longer a grade 10 thing. So we're hardly going to use that really. But it's quite important to know, because we are going to delve a little bit into conditional probability. So I want you guys to take a screenshot. When you're done, give me a thumbs up. Give me an emoji on the screen if you're writing it down. Also, give me an emoji on the screen when we are ready. And then we'll get started on what some of these things actually mean. All right. Hello, Letabo. Thank you so much for your thumbs up. Thank you, Desmarie. Okay. All right. 10 more seconds, and then I'm gonna get going. All right. All right, lovely. Okay, there we go. So let's talk a little bit about the different types of probabilities that we've learned so far, or the different types of identities that we've learned. So we've learned about the union. Remember, we learned about the union. Let's say, for instance, this is S, our big set S. This is sample A, B. Those are our subsets, subset A and subset B. Now, if we said we wanted, or let me start with the intersection rather. If I said I wanted the problem, or A intersection with B, oh, my mind is, whew, and it's only Monday. A intersection with B, right? We would know that the intersection is the part right here in the middle, right? It's the part where these two things meet. And there's another word for intersection. Do we remember what we said intersection is actually called? In like normal layman's people's terms. When we're not using funky words like intersection, what does intersection actually mean? Hello, Wikanyo. Lovely to see you. There's a particular word that I'm looking for. Okay, it's either going to be and or not. Which one is it? That's it, Fortunate. Lovely. It's and. Good. The intersection represents the word and. Okay. And when we look at the idea of the probability of, or let's say the probability of A and B, both of these things are conditional. Okay. And I'm going to explain what I mean by conditional when we get to the next part. Okay, we're just going to hold on to conditional for now. All right, now if I said I want a union B, what's another word for union? What's the easy word for union? Or. Good. Oh, well done. Fortunate, you're on fire today. Good. Or, right. So we know that if we want the probability of A union with B, we're also going to have a bit of a condition. It's going to be a little bit conditional, but it's very important that we remember that the probability of A or B includes both the probability of A and the probability of B together, right? Both of them together. Because when we look at or, remember, guys, we are basically saying the probability of A or the probability of B. It's everything all together. All right, so here's the kicker though. If I'm calculating the probability of one or the other, I can say that the probability of A or the probability of A or B would be the probability of A, right, which is this part, plus the probability of B, which is that part, right? Those two together make up the probability of A or B. But now I've got a bit of a problem. I've got a problem in that when I calculate for the probability of A or B, I've counted the middle part twice. I've counted it twice. I counted it when I looked at the probability of A, and I counted it when I looked for the probability of B. So if I'm calculating for the probability of A or B, I need to take the probability of A plus the probability of B minus the probability of A and B. Okay, I need to minus one of them because I can't count it twice. Okay, give me a thumbs up. Are you guys understanding why ma'am is minusing the probability of the one over the other? Making sense? Right, because if I calculate, Desmarie, are you, okay, Desmarie says, no ma'am, explain again. All right, I can explain again. So when I talk about or, let's talk about A or B, right? A or B, which is the same as A union B, right? Do you guys agree with me that the probability of A or B must be both of these together? Yes, thumbs up. Everyone okay with that? Yes? Lovely. That is A or B, all of it all together. Now, if I want the probability of an event in A or in A or B, I'm going to have to calculate the probability of A, the whole of A, right? And I'm going to have to add to that the probability of B. Okay, so now if you look at what's happened here, the probability of A has taken up that part, right? But also the probability of B has also taken up that part. How many times did we count that middle part? We counted it twice for each circle. Is that making sense? Right. So the only way for me to compensate for that is if I minus one of them. And we know that this middle part over here is called the intersection, isn't it? It's called the intersection when we're just looking at that part. And we know that the intersection is known as A and B, the probability of A and B. That's why we have to minus one of them. Wikanyo, Desmarie, are you guys with me there? We all good? Lovely, good stuff. All right, so when we calculate the probability of A or B, the probability of A plus the probability of B minus one of them because we've counted the middle part twice. Okay, all right. Now let's talk about mutually exclusive events. All right, and I know you guys did mutually exclusive with Teacher Kirsty last Wednesday. Who can remind us what does mutually exclusive mean? Or even if you don't quite know, you could maybe give us an example if you're not sure of the definition. Who remembers what mutually exclusive means?
They don't overlap and they have no common elements. They cannot.
That's it. Correct. Absolutely spot on. Right. So my two subsets do not overlap at all. Okay. So it's almost as if we've got I'm trying to get to that. Right. We've got A and we've got B like that. Right. Like that. Okay. So I've got set A, subset A, and subset B, and neither of them make up part of the other. So one cannot happen while the other happens. Okay. Each event happens on its own. Right. Happens on its own. Like, let's say, for instance, we're flipping a coin, right? I cannot get heads and tails at the same time. That makes no sense. Okay, so flipping a coin and getting heads and getting tails, those two events are mutually exclusive because I can't have one and the other. There's no and for both of them. They're not going to overlap. And in this case, then, if I did calculate for the probability of A or B, A union B, then I can just say that the probability of A or B for mutually exclusive events is just going to be the probability of A plus the probability of B. do I need to minus the probability of A and B? Would I need to do that? Yes or no? Okay, Buikanyo says no. What are we thinking? Do I need to minus the probability of A and B? No. Fortunate also says no. And you guys are spot on. Why do I not need to minus that? Because there is none. It's the same as me minusing 0. There's no point, right? So when we have mutually exclusive events, those two would not overlap. Okay, so there wouldn't be a minus P, the probability of A and B. It will just be those two. Okay, then we need to talk about the complement, and I'm realizing I've run out of space because I've written too big. Let me see if I can do this. Okay, I'm going to do this. I'm going to say mutually exclusive events. What we're looking at, mutually exclusive events. That means that the probability of A union B, which is the same as A or B, must equal just the probability of A plus the probability of B. And we don't have to minus anything because there's nothing for us to minus. There's no overlap. All right. Then we need to talk about the complement, right? What's another word for the complement? Who remembers? The complement, what's the normal? That's it. You're fortunate. What else? No, that was the answer for the thing before. What is another word for complement? It's not quite correct now that I realize it. Who remembers?
Ma'am, is it complementary?
You could say it's complementary, but that's when we're talking about angles, like geometry, like equal to 90. It means something completely different in probability. Did we forget what the complement means? I'll give you guys a hint. It's when we do this, when we go A apostrophe. Do you remember what the apostrophe means?
Oh, yes.
What does it mean?
A. That they are not A.
It means not A. Good. That's it. Right. Lovely. It means not. Good. So the complement means not. So if we want the probability of a complement, not A, we need to take the probability of everything and minus the probability of A. Because remember, everything, the probability of everything that we're doing in a specific event needs to equal 1. So the complement would be 1 minus the probability of A, because that would be not A, right? So if our A is equal to 1/3, right, the probability of not A is just going to be 1 minus 1/3, which would equal 2/3. Okay, and that's just a simple example. All right, thumbs up. Are we all happy with these definitions for probability? All good? Lovely stuff. Okay, we're going to have to put some of this into practice because we can't just talk about it and then not actually use it in anything. Let's look at what it looks like. All right, let's start with conditional probability. And the conditional probability we're going to be looking at today is this thing over here. Probability of A such that B. And this thing actually means such that, or in the event that B. Okay, and what this actually tells us is we're looking for the probability of A in terms of B. If B happens, then A will have to happen. So these two, or if B has happened, then A can happen. And these two are inclusive, mutually inclusive events. Okay, they are mutually inclusive, but we're not going to be using the formula here. We're just going to be remembering that A is the condition, or B is the condition that A is under. So we calculate the probability of A such that B has happened. Let's say, for instance, you want to go wash your car, right? So in order for you to wash your car, it needs to not be a rainy day. So the probability of you washing your car, A, is dependent on the fact that B did not happen. But if B does happen, then your probability of A is going to be less. That is the conditional part of it. Okay. Now, this can manifest in more than one way, and I'm going to show you exactly what we mean. Okay, there we go. Formal definition of conditional probability. For any two events A and B, the conditional probability of A given B may be calculated by this. Okay, so I want you guys to have a look here. This is the probability of A and B over the probability of B. And we're going to be looking at that in a little bit more detail as we go along. But for now, please just take a screenshot of this and I'll explain it a little bit further as we keep going. Okay. All right, Fortunate says all good. Okay. All right, so let's talk about what conditional probability actually means, because it's basically just a fancy way of us saying that we're looking at dependence and independence. Okay, because the probability of the one will affect the other. So let's think about this. If I flip a coin, pop your answer in the chat. What is the probability that I would get heads? If I flip a coin, what is the probability that I will get heads? %, good, or 1/2. Thank you, Sally. Good, Oko. Right, the probability of me throwing heads is 1/2. Okay, now I go to flip the coin again. What is the probability that I'll get heads the second time? It's still 1/2. Nothing has changed, right? It's still 1/2. Right, it's still 1/2. So nothing really changes. The probability of the first thing happening doesn't affect the probability of the second thing happening. And we call these two events independent events because they happen completely devoid of the other. If the other one doesn't happen, it doesn't matter. It won't affect what happens next. But if we think of the wash your car analogy that I just gave, the probability of rain is going to affect the probability of your car being washed, right? So these two, because they affect each other, they are called dependent events. Okay, thumbs up. Everybody okay with the difference? Independent and dependent events. Are we all good? Okay, lovely. And that's kind of the basis of conditional probability. It comes from the idea that an event is either dependent or independent. Okay, and we'll see which one of those we get. So let's look at this very simple example over here. Okay, it says, suppose we have a box that has 3 red marbles and 2 black marbles. We select 2 marbles. So this selecting of 2 marbles gives us the number of events. This tells us that there are 2 events that will take place, right? First, we'll pull out a marble, and then we'll pull out another marble immediately after that, right? So let's talk about event number 1. In event number 1, what is the probability of the first one being red? What is the probability of me pulling out a red marble? Okay, first we need to look at our event number. How many events do we have? We want red. How many red marbles do we have? We want to see that we're pulling out a red marble. How many red marbles do we have? We
3.
have 3. Good. We have 3 of them. So our event size is 3. What is our sample size? What are the possible outcomes? How many marbles do I have altogether?
7, 2.
Not 7. Let's count them. It says here, I've got a box that has 3 red marbles and 2 black marbles. How many marbles is that altogether?
5.
5, good. So our sample size is 5, right? So an easier way for me to put this is if we had to do our sample, let's say we've got our sample, we've got a box, right? The box is our sample. Inside the sample box, I've got a red marble, a red marble, a red marble, and then inside I've also got a black marble and a black marble. That is my sample size. Now, my event underneath that, my subset, is going to be the red marbles. So I know that there are 3 of them. 1, 2, 3, right? So my sample size is how many elements do I have in here? 1, 2, 3, 4, 5. I have 5 of them. And my event size is how many elements do I have in my event? I have 3
3.
of them. Good. So what is the probability that I would take out a red? What is the probability that I would pull out a red marble? It would have to be the event over the sample, right? Because probability of any event is the event size divided by the sample size. So that would have to be 3 over 5. Is everybody with me here? Are we all good? Okay, Buikanyo's a little lost. Okay, let's try and explain again. Okay, so we're going to read the first part. Let's read the first part. Okay, the first part says, I have a box, right? I have a box. And inside this box, I've got 3 red marbles and I've got 2 black marbles. Okay, how many marbles do I have in my box altogether? I have 5 marbles, right? I've got 5 marbles. Right. Now, if I've got this box and I put my hand in, what is the probability that I'd pull out a red marble? That means I need to figure out how many red marbles I have out of all the all the marbles that we have. Now, I've got 3 red marbles out of the 5 red marbles or the 5 marbles in the box. So my probability of pulling out a red marble would have to be 3 over 5. Okay, Buikanyo, are we good here? Lovely. Okay, now herein lies the problem. Herein lies the problem. The problem is that even if we pull out a red marble, right? The question here says, what is the probability that the second marble is red given that the first one is red? Okay, so now if I pull out a red marble, what is the probability that I would pull out a red marble again? I've got a problem, right? Here's my problem. I don't know whether in the first event, whether I pulled out a red marble or a black marble. Am I making sense? Thumbs up. Yes, everybody okay with that idea? I'm not sure what happened in my first probability or in my first picking of a marble. So I can't be sure what the probability of the next one will be. Okay, I just want to make sure. Does everybody understand the statement that ma'am has just said? Okay, cool. All right. So in this case, we need to use the idea of conditional probability because we are looking at the fact that the first probability affects the second. We don't know whether it's dependent or independent because we don't know whether we pulled out a red marble or a black marble the first time. Oh my gosh, guys, and I'm just realizing I've completely forgotten to give you the formula. Oh, guys, I'm so sorry. The probability of A and B, my apologies, guys. The formula for this over here, for probability of A and B, would have to be the probability of A times the probability of B. I'm so sorry, guys. It clicked to me now that I hadn't actually given you guys the formula. Please write that down. Please write that down. Okay, those are all the formulae that we need. My word. Sure, guys, it's a Monday. It's a Monday. I hope you guys will forgive me. I'm working at half speed clearly today. Okay, so the probability of A and B is the probability of A times the probability of B. Okay, now let's go back to the question at hand. So remember that conditional probability tells us that if we want the probability of A given that B has happened, so we want the probability of the second marble being red given that, do you see there's the statement, given that the first one is red, we're not going to be able to do one after the other. So we need to say the probability, we need to write the probability that the first one is red, given that the second one is red, given that the first one is red, is going to be the probability of our first event and B. So we need to take the two and multiply them. So we need to say the probability of red times the probability of red, because those are both of, that's A and B, right? Let me just rewrite this here. The probability of A and B must equal, I'm doing great today, guys. The probability of A and B needs to be the probability of A times the probability of B. And that's why where I see probability of A and B, I'm splitting it into probability of red times the probability of red over the probability of B. Now, I know that my second event is also the probability of red. Okay, let's put all of that together. Okay, we said that the probability of pulling out a red marble is 3/5. I want you guys to punch this into your calculator. The probability of red is going to be 3/5 times the probability of red, which is still 3/5, all over the probability of red again, which is also 3/5. Please punch that into your calculator and get me an answer. What do we get, peeps?
3/5.
We get 3/5 again, correct. So the probability of both events, one happening because of the other, is 3/5. Okay, I feel like this example was very messy. Shall we do another example? I think let's do another example just to solidify where we're going with this. Okay. All right. Oh, this one is too easy. That's just dependence and independence. Let's look at conditional probability. Give me a second. Okay, let me just take a screenshot of this very quickly and then we can work on this. Sure. Guys, sometimes, you know what? Technology is just not your friend. Sometimes technology is not your friend. Okay. All right, there we go. Let's pop this here. Okay, let's look at this over here. All right, so it says, below we are given a Venn diagram showing events A and B. Now it says, calculate the probability of B given A. Now we need to be very mindful of the order in which they've given this to us, because the probability over here, or the equation that we have for probability, says the probability of A given B. So if we have to rewrite this formula for B given A, we're just going to go, the probability of B given A is going to equal to the probability of, that part is not going to change, A and B, but instead of it being over the probability of B, it's going to be over the probability of A. Thumbs up. Everybody okay with what ma'am has just done here? Yes? Okay. Just because whichever event comes first, that's the one that we're putting together. All right. Okay, so let's go back to the example. All right. So here's the two things we're going to have to find. Remember, when we calculate for the probability of any event, we first need the event size divided by the sample size. Now, at the moment, we don't have the sample size. Let's figure out what is the sample size. Somebody add up for me and give us the sample size.
23.
Not 23, you missed it by just a little bit.
25.
25, there it is. Good. Don't forget this little 2 sitting on the outside. It's also part of that. All right. So our sample size is 25. Okay. So now they want the probability of B given A. Now, we know that the probability of B given A is just going to be the probability of A and B all over the probability of A. Okay, now the nice thing for us is that we know that our probability of A and B is just this part over here. Now, this is not the answer. This is our event size. This is our event size for A and B, right? So when I say the probability of A and B, what is my answer for the top actually going to be? The probability of A and B needs to be how much? Not just 8, it would have to be 8 over something. What is that something? 8 over, remember, the event size over the sample size. How much is our sample size?
Oh, 25.
Over 25. Good. That's it. So the probability of A and B needs to be 8 over 25 divided by the probability of A. So the probability of A now is going to have to be all of this. This is my entire event size. So what is the probability of A going to be? Remember, this is my event size. What are we looking at? 11 over, remember, it's not just the event size, it's the probability of the event. That's it, Letabo, lovely. It needs to be 11 over 25. Okay, let's punch that into a calculator and get me an answer, folks.
8 over 11.
8 over 11. Good. So our answer will be 8 over 11. All right. Thumbs up. Is this making a little bit more sense? Are we all good here? So Ofato says yes. Everybody else? Lovely. Let me see if I can get you guys an example to do for yourself. Okay. So I'm going to give you guys this Venn diagram, and I want you guys to answer. I want you guys to calculate for me. Calculate the probability of piano given that they play, that the student plays violin. This is students. So there are two things that we're going to have to figure out before we even start. First thing is the what?
Sample size.
That's it. Yay, we need the sample size, right? So if we're looking for the sample size, we're just going to take everything, add it all together, right? How much is my sample size? $24. That's it, Sally. Absolutely. 8 plus 2, that's 10 plus 10, 24. Right, 24. Now, remember, guys, the probability of piano given violin is going to equal the probability of piano and violin over the probability of violin. Okay, or did I get that wrong? No, I'm correct. Probability of violin. Okay, punch that into your calculators, guys, and give us an answer. Remember, the event size is that. That 4 is just the event size. It's just NE. It's just the event size. And remember, when we're looking for the probability of the event, that is the event size divided by the sample size. All right, pop your answers in the chat for me when you're ready. Okay, good, fortunate. So the first part will be 4 over 24 over what? Over what? Okay, so I'm going to guess that's the final answer. Yes, is that the final answer? Let's see if everybody agrees with you. Okay, let's have a look. All right, so I agree with, I agree with Fortunate that the probability of piano and violin is going to be 4 over 24. And all of this must be over the probability of violin. So violin is 4 and 2 put together, that whole thing. So that's going to be 6 over 24, right? And if you punch that into a calculator, we should get, I'm getting 2 over 3. I don't know about 1 over 6. What does everybody else get? 1 over 4? Let's see, 4 over 24 divided by 6 over 24. I'm getting 2 over 3. Okay, how did we do, guys? Sally, how did we get 1 over 4? Okay, I'll tell you guys what. I don't know how that's possible. Okay, Sally, let me show you, because I can do this in my head very quickly. I can go 4 over 24 divided by 6 over 24. What's going to happen is I'm going to tip in times. So I'm going to get 4 over 24 times 24 over 6. And if I cross cancel, the 24s will cancel each other, and I will have 4 over 6 left, and that will translate to 3. So that makes sense to me. I don't know how everybody else got a different answer. Or maybe I did something weird. Let me see. 4 over 24 divided by 6 over 24. No, I still get 2 over 3. Fortunate says yes. Sally, do we see where we didn't quite? There we go. Now it's making sense. Okay. All right. Okay. I'll tell you guys what. On Wednesday, because that will be us doing the last bit of probability, we'll do a little bit more practice on these kinds of questions. All right. We can get to those questions then. All right. So I want us to actually put these formulas that we're learning into practice, which is what we're actually going to do today. All right. So we've been given the following. It says here, if the probability of A is 0,3 and the probability of B is 0,5 and the probability of A or B is 0,7, find the probability of A and B. Okay, so let's put this all together because it's going to be a little bit trickier than what we're thinking. Okay, so we know that we've got 2 events. We've got A and we've got B. Okay, now the sample size of any probability or the probability of a sample, let's put it this way. How much should the probability of a sample equal? Like all together, how much must it equal?
1.
1. Beautiful. Was that you, Unati?
Yes, that was me.
Ah, well done, lovely, good. The probability of an entire sample needs to equal 1, lovely. So now we're going to have a bit of an issue, right? If I take all of these things and I add them together, they're not going to give me 1, right? 0.3 plus 0.5, that's already 0.8. And if I add 0.7 in there, that's going to give us 1.5. So we're not 100% sure what that's going to be. What we do know is that the probability of A all itself needs to be 0.3. The probability of B all itself needs to be 0.5. And the probability of these two things together must equal 0.7. So somewhere, somehow, we must minus somewhere to get where we need to go, right? But we don't know yet where to minus. What we do know is we have a formula. We have a formula for the probability of A or B. And luckily for us, we can tell over here that this part is an intersection, which means there's and. It's not mutually exclusive. So what I'm going to do is I'm going to go the probability of A or B is equal to the probability of A plus the probability of B minus that extra intersection where they come in, probability of A and B, right? And because we're calculating for the probability of A and B, we are going to make this part the subject of the formula. So we're going to go ahead and replace all the other things with what we have, and then we're going to solve for the probability of A and B. Thumbs up. Am I making sense? Is everybody okay with this idea? Yes? Let's substitute and let's see what happens. The probability of A or B is going to give us 0.7. And that would equal the probability of A, which is 0.3, plus the probability of B, which is 0.5, minus the probability of A intersection B. That's the thing we're trying to figure out. So we're going to take everything else over to the other side, right? Basic math. All of that stuff must go over. So we're going to get 0.7 minus 0.3 minus 0.5 must equal the negative probability of A union or intersection B. Somebody put that into a calculator and give us an answer. What do we get?
Negative 0.1.
Correct, negative 0.1. So we'd get negative 0.1 equals negative probability of A intersection B. So as soon as we see that there's a negative and a negative, we can drop the negatives, right? So both of these out. Okay? So that means that the probability of A and B, the probability of A intersection B is 0.1. So this part over here will be 0.1. Everybody okay with this? Thumbs up. Are we cool with what ma'am has just done here? Lovely. Cool stuff. All right. But now let's remember what we know. If the probability of the whole of A is 0.3, 0.1 has already been accounted for. What is the probability of A only? What is the probability over here going to be? If the whole thing must be 0.3 and 0.1 has already been accounted for, what is the little bit going to be that's left? It's not a trick question, guys, I swear. It's just going to be 0.2. Does everybody understand why ma'am says 0.2? Yes? Right? If the whole, okay. Okay, fortunate is a little bit lost. All right, so they're telling us that the probability, sorry, we've just calculated the probability of A and B is 0.1, right? This statement over here says the probability of the whole of A is 0.3. The whole of A includes that 0.1 that we've just calculated. This whole thing together must be 0.3. We've already got 0.1 in the intersection. What is left over the thing that's left over needs to be 0, 2. Does that make sense? Fortunate, we got your week, okay? Okay, cool. Now let's look on the other side. Let's go ahead and look on the other side. On the other side, it says that the probability of B must be 0, 5. Now, if I isolate the whole of B already has 0, 1 accounted for. What's here? What goes there? That's it, Letavo. That's it, Sally. Beautiful, fortunate. Good. 0, 4. Yes, correct, Balesa. That's exactly what we needed to do. Right. So this part is going to be 0, 4. And we're going to see that our mathematics actually checks out, right? Because the equation here says the probability of A or B, which would be all these things included together, all of that must equal 0, 7, which is, it does now. 0, 2, 0, 1, 0, 4. If we add all three of these, that becomes 0, 7. Do you see how it checks out? Yeah, we're all good, everyone? Lovely stuff. I've got a bit of a problem. 0, 7 is the inside. What needs to go on the outside of my two circles? That's it, Desmarie, lovely. Because the probability of my entire sample must be 1, I only have 0, 7 accounted for, which means on the outside of my two circles, maybe over here, we must have a 0, 3. Okay. How are we doing, folks? Are we okay here? Yeah? Okay, lovely stuff. Let's answer some of these other questions. Okay, so we know the probability of A and B. We've just calculated it. That's 0, 1. We did that up there. Right, now it says the probability of not A and B. Okay, so let's go and let's have a look. What is not A? Okay, we know that, oh, sorry, let's just hold on. We know that the probability, when we're calculating the probability of and, the probability of A and B, oh, that's an ugly way to put and. Oh, my maths professor would kill me. A and B, right, is going to be the probability of A times the probability of B. But now let's remember what we've said about not. Not is going to be 1 minus something. Yes, 1 minus the thing that we have. So we're going to say the probability of not A is going to be the probability of 1 minus A, right? Times the probability of B. Is everybody okay with this? Thumbs up. Are we okay with what ma'am has just done here? Yes. I told you those equations, those identities we were using are going to come in handy over here. Okay. So we now have to do the probability of 1 minus A. So we're going to go the probability of 1 minus, how much is A? Altogether, A is 0, 3. So we need to go the probability of 1 minus 0, 3 times that, sorry, I don't need this part anymore because the probability is just 1 minus 0, 3 times the probability of B, which is 0, 5. Let's punch that into our calculator and get an answer.
0,35.
That's it. Well done, my darling. 0,35. Okay. All right. I'm going to ask you guys to do B really quick. I think we should have gone A, B, and then C, and then D. That's fine. Let's do B. The probability of not A. So we know that the probability of not A is just the same as 1 minus A. And we know what A is equal to, or 1 minus the probability of A. And, okay, and that's going to give us 1 minus A is 0, 3. Therefore, that gives us 0, 7. Okay, I want you guys to try D for me. Pop your answer in the chat once you have an answer for D, and let's see if you guys can get it. Okay, I'm going to remind you guys that in the middle is not an and, it's an or. So we need to remember the formula for or. I'm just going to put it over here. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, remember that. Anybody managed? You can also just be like, yo, ma'am, me, I don't know. It's fine to be like, hey, ma'am, I don't know. It is a bit of a tough one. I'll tell you guys that for a fact. Oh, Fortunate figured it out. Well done. Let's see if we're all going to agree with each other on the answer, though. Okay, shall we have a look at the answer? If we're stuck, it's fine. It's fine. Okay, so I'm going to redefine this very quickly because we need to make sure we know exactly what it is that we're doing here. Right? So if we're looking for the probability of not A or not B, then this formula changes a little bit in that probability of not A or not B is going to be the probability of not A plus the probability of not B minus the probability of not A and B. Okay, so that not A and not B. Okay, so, or not A and B altogether, really. Okay, so we need to make sure that we're doing this correctly. So the probability of not A is going to be 1 minus A, which is 0.3, plus the probability of not B is going to be 1 minus 0.5. And all of this is going to be minus, now the probability of not A or B is going to be 1 minus that, because that is A or B, right? So that's going to be 1 minus 0.1. And the answer we should get from this is 0.3. How did we do? Did we manage? Yes, no? Thumbs up, thumbs down. Yes.
Ma'am, I just got 0.3, but I didn't know like the calculation. I didn't use the formula, but I just wrote it as in straightforward 0.3. So like,
Okay.
will I lose marks for that?
How did you get there? How did you get there? Because the method is the mark. I'll be
Ma'am, because
honest.
I used the Venn diagram so I could see that the rest of them were in the circles, and then the one that was not, the excluded one, was only 0.3.
Okay, you know what? I'll give you that. I will give you that, especially because it's the probability of A or not A or not B. So A
Yes,
or
ma'am.
that whole thing. So the rest of it is just 0.3. I will give you your 3 marks. I will give you your
Okay.
marks. Well done.
Okay,
That was
thank you,
actually
ma'am.
okay. It's going to be a little bit problematic when we get to a question like this, where there is no Venn diagram. Okay, when we don't have a problem, now we're going to have a bit of a problem in that we don't quite know, but we can take information that we've been given and we can use we can use the information that we've been given to draw a Venn diagram because we know our identities and we know what goes into our Venn diagrams. Okay, so let's read this particular question over here. It says, a boy has 0.19 probability of winning an art competition and 0.13 probability of winning a talent competition. So we already know that if we were to draw a Venn diagram, we'd have two circles. We'd have one circle there, and we would have another circle there, right? For two things. One would be the art competition, and the other would be the talent competition. Okay, so the whole of the art competition is 0.19. That's the probability. The probability of the talent is 0.13. Right. Now it says, suppose he has a 0.11 chance, that's supposed to be chance, of winning both the art and the talent competition. So we already know that our and part, the and, is 0.11. What goes there? Who can tell me what goes over here? In just A only. I'm hoping so. I'm hoping so. It's a very short one.
Yes.
Good, Stanley. Not 0.8. You've missed it by just a little bit. 0.08. That's correct. Let me just make sure I'm not lying. Yeah, 0.08. So this side will be 0.08, and on this side would be on the other side.
0.02.
That's it, 0.02. Good, 0.02. Now let's add all of this up together and make sure that our probability altogether would add up to 1. It needs to add up to 1. So if I add everything that I've got over here, 0.08 plus 0.11 plus 0.02, that gives me 0.21. That only gives me 0.21 here for A or T. So what needs to go on the outside? I know that the probability of my sample must equal 1. If everything on the inside equals 0.21, on the outside of my two circles, I would need 0.79. Thumbs up. Is everybody okay here? Everybody okay with what ma'am has done here? Lovely. I want you guys to answer the questions for A for me. They're very, very quick. You'll be done in 3 seconds, trust me. Or shall we do it together? Because we've got less than a minute left. Okay, now it says, define the events. The boys win, or the boy wins the art competition. So the probability of A, okay, it's just 0.19. The probability of A is just 0.19. The probability of winning the talent competition is just 0.13. And the probability of A and T, as we've established, is 0.11. The next question says, are events A and T defined, or yes, defined in A mutually exclusive? This is a yes or no question. Yes or no? Are they mutually exclusive? What do we think, guys? Ah, good, Vanessa. Yes, good. Or not yes. No, you are correct. The answer is no, because he can do both. He can win both the art and the talent competition. So no, they're not mutually exclusive. Okay, it says, what is the probability that the boy does not win the art competition? So they just want the probability of not art, right? The probability of not A, and that's just going to be 1 minus 0.19. Okay, what is the probability that he wins the art competition or the talent competition? So let me finish up here. This is 0.81. All right. Then they're saying the probability that he wins the art or the talent competition. So the probability of art or talent is going to be the probability of art plus the probability of talent minus the probability of art and talent. Okay, and we can finish this up in the next lesson. You were quite right, Desmarie, we were not going to finish on time, which is fine because we still got Wednesday. All right, this is where I'm going to call it for today.